So now consider a simple magnetic circuit like this. So if you consider a simple magnetic circuit where this is an iron core or a core, so this is a core now of length L, and a coil of N turns is wound on one limb of this core. This is called as a limb. దీన్ని limb అంటారు ఈ portion ని. This portion we call it as limb of this core, right? And a coil is wound with n number of turns, and when a current I is passing through this coil, and if you apply the Fleming's right hand rule, stretching your holding this coil with your right hand in the direction, the current direction, you keep your all four fingers in the direction of keep your right hand four fingers, you keep your right hand four fingers in the direction of current, all the four fingers except thumb, and stretch your thumb, and therefore, and keep, if you hold the coil with your all right hand four fingers, that is index finger, middle finger, ring finger, and the little finger, with all the four fingers you hold your coil. If you hold your coil here, this one, if you hold your coil in the direction of current, keep your, then your thumb direction would be in this one. అప్పుడు తంబు ఈ మనం చేతోటి దీనిలో పట్టుకుంటే తంబు డైరెక్షన్ పైకి ఉంటుంది, and therefore the thumb direction would give you the direction of flux. If you keep your all four fingers in the direction of current in the coil, and the thumb indicates the direction of flux, that is the Fleming's right hand rule, or Fleming's thumb rule అని అంటాం. Fleming's thumb rule, it is called as a Fleming's thumb rule. So if you apply this Fleming's thumb rule to here, then you will get the flux direction like this. So for this, we call it as a series magnetic circuit, because why we are calling it as a series magnetic circuit here? See here, this magnetic core will have different parts. This we call it as part 1. ఇది part 1, ఇక్కడ నుంచి ఇక్కడికి part 1 అనుకోవచ్చు. P1 I call it as. ఇది part 2, ఇక్కడ నుంచి ఇక్కడికి part 2, and ఇక్కడ నుంచి ఇక్కడికి part 3 అనుకోవచ్చు. And this portion we call it as part 4. Now in this example, all the four parts are equal కాబట్టి, అంటే part 1, part 2 and part 3 are equal, since మనం సేమ్ ఏరియా ఆఫ్ క్రాస్ సెక్షన్ తీసుకున్నాం కాబట్టి part 1 is same as part 2, is same as part 3, and it is same as part 4, and the total length is L. Yeah, this is here area, since area of cross section of all these quantities A1 is equal to A2 is equal to A3 is equal to A4 is equal to A. Therefore, when their area of cross section is same, then what about the reluctance expression? S is equal to L by mu naught mu R A. This is the expression for the reluctance. We have derived it, and wherein L is same, area of cross section is same, mu naught is okay, is absolute permeability is common for everyone, and relative permeability also same when this core is made up of same material, when the entire core is made up of same material. Therefore, the reluctance will be a constant, only one reluctance, and that could be represented as an electrical equivalent of this, or an electrical analogy of this is represented like this. This is representing, this resistance symbol is representing the reluctance in the magnetic circuits, right? And here you are applying a current, and that is why it is representing a source, and this source is, we call it as MMF. In electrical circuit we call it as EMF, and but this is a magnetic circuit, and it is given by MMF, and the MMF is given by N into I. Therefore, this is given by N into I. Therefore, this simple series magnetic circuit is represented with a electrical equivalent circuit like this: a voltage source in series with a resistance, or an MMF in series with a reluctance. And this reluctance, and we also know that the MMF is equal to flux into I. So since the current is same, since it is, see here the flux is same in this entire magnetic core, and therefore the flux is same. That is why it is called as a series magnetic circuit. So the flux is, therefore this flux is resembling the current in magnetic electrical circuit, and it is given by, see here the MMF is given by the expression MMF is equal to Ni, and which is equal to phi into R or phi into S, both are same, which is also equal to H into L. H into L is also same, where H is the flux intensity. So let us consider the another magnetic circuit like this. See here, ఇందాక మనం తీసుకున్న magnetic circuit లో మొత్తం సేమ్ ఒకటే magnetic core ఉన్నది. ఇక్కడ let us take another magnetic circuit wherein you have a magnetic circuit with an air gap here. Here you have an air gap, a cutting here you have with a length of a gap. This iron core has got a cutting of length with a length of Lg, and the remaining length of this iron core is given by Li. Therefore, the same series magnetic circuit earlier will be now split into two parts. The lengths will have two lengths. We have one is Li and Lg. When the lengths are two lengths, but the area of cross section of these two is same, that is Ai is same as Ag. Therefore, what about the reluctance? Reluctance of the length I, this one, the reluctance between I say the I start from PQR, the reluctance of PQRSTU path. The reluctance of PQRSTU path, I defined it as SI. ఎందుకంటే ఇది మొత్తం ఇదంతా ఒకటే లెంత్ తోటి ఉంది, ఒకటే మెటీరియల్ కాబట్టి ఈజ్ గివెన్ బై LI by mu naught mu r I into AI. Since AI is same as AG and it is equal to the AI call it as, then what I can write here it is LI divided by mu naught mu r I into A. This is the reluctance. This is the reluctance of the iron path. So this is the reluctance of this your iron path. Reluctance of iron core. Iron core. Now the second part here it is air gap you have. So now let us find out the reluctance of air gap. So reluctance of air gap is equal to, I designate that as SG gap is equal to, as per the formula, LG by mu naught mu r g AG. Then this we can be simplified as LG by mu naught. What is mu RG? Mu RG is the relative permeability of the air gap. What is the relative permeability of air? The relative permeability of air is given by 1. The relative permeability of the air is always 1. Therefore, you will have only mu naught into A. Since AG, here we have defined it as AG, AI, and is equal to A. Therefore, this is the expression for the reluctance of the air gap. Now here, your simple series magnetic circuit, in this series magnetic circuit, it is since it is offering two reluctances. Therefore, and they can be represented, this SG and SI are represented in the electrical analogy as RI and RG here. And this RI is same as SI and RG is same as SC. So therefore, there are two resistances connected in series with a MMF, with an MMF given by N into I. And the flux in these two reluctance paths is same since they are connected in series. And the MMF across the iron path is given by HI into Li. What is this HI into Li? HI into Li is the MMF of iron core is given by HI, that is intensity of iron core into Li. Similarly, MMF of air gap, that is G, is given by Hg into Lg. That is what here it is written. Please look at that. So that this MMF we can represent, we can say that in case of electrical circuit, this is like a voltage drop Vi, and this is also like a voltage drop Vg. Voltage drop across the iron core plus voltage drop across the. Therefore, the total MMF is equal to what we can write here. It is total MMF if you apply the Kirchhoff's voltage law, like electrical circuit. MMF total MMF is equal to MMF I plus MMF G. So we can say that MMF I plus MMF G, like Kirchhoff's voltage law in electrical circuit. If you apply this MMF, therefore the total MMF applied to MMF is equal to MMF across iron core and MMF across iron core MMF I plus MMF G. So this is about the series magnetic circuit. Now for this circuit, basic equations can be developed like this. The number of turns are given by this. The number of turns are given by N, and the exciting current, total exciting current is in I amperes. And the mean length of the flux path of the iron core we have designated as Li, and the length of flux path through iron core is given as Lg. Then area of cross section of the iron core is given as AI. Then if the cross sectional area, A is constant throughout, the flux density would be constant because A is constant and flux is also constant since it is a series magnetic circuit. Therefore, the flux density will also be constant both in iron and air path. Since the value of permeabilities are different for iron and air, the corresponding values of HL and Hg will be different. అంచేత ఎందుకు permeability వేరు కాబట్టి. So what is HL or HL or HI is given by B by mu naught mu r I. Since B is constant because of that, therefore it is depends on this one. Uh, and similarly, Hg is equal to B by mu naught. Mu r for air is 1. Therefore, mu naught into 1 into that is 1 only, mu r. That's it. So B by mu naught is the. Therefore, overall, your, as I mentioned earlier, total applied force Ni is equal to HL into Li plus Hg into Lg. This is the formula we use, and then you'll get like your Kirchhoff's voltage law in electrical circuit. So the H required, as I mentioned earlier, the H required, yeah, H required is in case of iron is B by mu naught mu I, and H required for air is Hg is equal to B by mu naught. Since mu r of air gap is 1 all, since this one is 1. The Ampere circuit laws gives that, see here, it is just like our similar to, it is similar to KVL in electric circuits. So which is given by Ni is equal to HLI plus HLG, which I have explained here. And what is H into Li is equal to, see here, Hi is this is Hi into Li, and this is Hg. So our total, according to the Ampere circuit law, total MMF, that is Ni is equal to Hi into Li plus Hg into Lg. So I'll substitute చేస్తే మనకి, so now ఇలా వస్తుంది. Down in place of phi, if you substitute, sorry, in place of flux density B, if you substitute phi by A, here you'll get like this. And if you further simplify that, since phi is constant, phi and A are same in both the mediums, so then you can take a common as phi is it phi into 1 by mu naught mu I into Li by A. And now if you look at that, this is a expression is representing the reluctance expression, and it is reluctance path of iron core. And similarly, this expression we call it as, it is just like a reluctance path of air gap. And total Ni is equal to, I can write it as phi into Si plus phi into Sg. So that is represented here. See here. And in the phi common కాబట్టి, you take phi common, therefore Ni is equal to phi into Si into Rg. Now this we can write it as like this, where phi is equal to. So it is just like, see here, in a series magnetic circuit, current V is equal to total applied voltage V is equal to I into R equivalent, where R equivalent in a series magnetic circuit is given by R1 plus R2 plus R and so on, like this. In a similar fashion here also, see here, this is S equivalent. That is reluctance, equivalent reluctance. S equivalent is equal to Si plus Sg. All right. So this is how the series magnetic circuits are to be analyzed here. So therefore, for a series magnetic circuit having different reluctance segments, the total reluctance will be the sum of the two individual reluctance. So you can each what we can do. Therefore, the total reluctance of a series magnetic circuit is the sum of the reluctance, individual reluctances. That is the conclusion we can make from this discussion.